that many of you are not able to find the left null space. Is there any problem with getting that? That is simple step, no? You can follow. You just do the transpose and find the null space, or from the left side you can find the null space. However you want, you can do that. So what is so many of you didn't find the null space, left null space. Why? Why it is so? Finding the inverse, those all are diagonalization. That's totally fine. That is not a big issue. We have provided the marks. We thought it is a tough. Who wrote the steps got the marks also. But I have just one doubt. That is a 3-mark question of the quiz 2. The left null space. Many of are able to find the eigenvalues, eigenvector, but the first part. But the second part, I've seen. If I think I've checked 30 copies and only two, not two, maybe five. Five is going to be more. Only five maybe. Student wrote the left null space. Find the left null space. Why? Why it is so? Like you people don't know what is the left null space, or you missed that question. Anyone? No. Lucky, Rahina. Anyone? Could you answer that? Have you solved that? Anyone is here who have solved that left null space? No. Okay. So due to the left, I didn't write the full solution, so I directly write the. I don't need any marks. Okay. Raman Singh.
Yes, sir. The answer is maybe sir 000 now for left null space.
Yeah, probably.
Yeah, but I didn't get any marks. But because of the lack of time, I directly write the answer, but didn't get any marks.
Okay. Okay.
And in objective questions also, sir, if I am wrong in one option, then there should be
Mm-hmm.
2 marks for the correct option.
Okay.
But I got only one in each in two questions, sir. So I fill out the
So
discrepancy form
is
also.
no. The reason is if you do as as in the portal side, will this be followed? If you choose one wrong option, then it will give 0 mark, right? But here
Uh,
in
no,
subjective,
sir.
at least we are providing some marks.
No, so there is no negative marking, na, maybe.
No, not negative. If you choose correct option and with the wrong option, if you are choosing wrong option with correct option, then the marks will be awarded 0, as in the portal, right? Because you are choosing the wrong option. There is not negative. If you choose like B and C is correct, and you chooses B and C, and also one of let's say A and let's say D, any of you chooses or both you have chooses A and D also or A only, then your marks will be given 0, right? It is generally in the portal. The same case will follow. Otherwise, how you will feel that this is now you have to choose only the correct option. You have write the correct option. Okay, this is the only correct. You are choosing the wrong option also, then the marks will be reduced, right? So here it is a subjective, that's why I are providing marks. Otherwise, if it is a portal case, it will be 0 marks.
But sir, in quiz one, we don't have this rule, no?
No, this is the only rule.
But in quiz one, this is not followed, no? If we have one correct option, then there is half marks given.
Yeah, partial mark would be provided if you choose one person. If you correct, you are choosing the correct option. Like B and C is correct, you are choosing only B. Then the partial marks will be awarded. If it is 2 marks question and you are just choosing B, but the correct options are B and C, if you are choosing only B, then yeah, 1 marks will be given. But if you are choosing A and B, which where A is wrong, then 0 marks will be given. This is how the portal works, correct?
Okay, sir.
So the same it is following the same things. We are not thinking. Yeah, this is one benefit is there. Okay, we got that you are choosing wrong option with the correct option also, and you wrote some reasons there. Then we'll not given the full marks. Then there is no mean of that. If you are choosing wrong option also, then how it is? If you we will give only for the correct option, then it is kind of you will choose all option A B C D, and we will now select okay you are giving the this. If you choose A B C D always in the all options, then how will distinguish you are getting that? So this is that's why it is not done. So this is how it's portal done. Then we are doing this. From our side, we used to provide some marks. If we found reasonably you are getting your writing reasonable, that you are writing the steps or by mistake you made wrongness there, then we will surely provide the marks. That's the benefit of subjective. Okay. Mm, okay, that lack of time is, I think so. That is a big lack of time. Anyone is here also who faced this issue, or all of you face this issue? Lack of time. Yeah, I want to know many of you. Like 5 students have did this. Only they found left analysis. Yes, Rahina. Okay. So it's lack of time. Okay. This is one thing is there that, but in on steps we used to provide. And in the, okay, let's see how it could be in term. So in term, be ready with that. The same number of question would be there, and numerically that is not a big thing. If you are writing even some regions, certainly marks will be provided. Contain lambda is easy, but in quiz two is it's hard. Hmm. Oh, that is we know that. That's why we provided mark. No, if you are just writing the at least the characteristics, we provided marks more at most. Like if it is 1 marks would be given, but we provided 2 or 3 marks sometimes. Half of the marks even on the characteristics only, or 1/3 marks would be on the characteristic only. Okay, let's see how it could be for in term. But yeah, many people see one reason is there. All of you are not writing. All of you are not practicing. And one more reason I know. If you practice, if you're writing, if you practice yourself, then it would be good. Because there you have to think and solve. And graded assignment, if you're just copying some from somewhere, or then it will no need to think, just write. And if you are doing yourself, then there is no time limit. You have to just think and write. So, but you have more time, more than 2 hour, 3 hour, 4 hour, a day, full day, 1 week is there. But in term, you have to think and write both simultaneously. So it will be hard. But this is the exam. This is the meaning of exam. Without practice, you cannot do. Okay. So let's back to this content of week 10. So in week 10, only one lecture have covered, and week 2 we have a DFT, discrete Fourier transform, and And the second thing is their computer on linear algebra that is done by Prof. Yun. We no need to discuss that. And next is the normal operators. So in DFT, what we will collect, no, this is just a diagonalization. So in lecture one, we have seen what is a circulant matrix. This is just matrix of some whatever we are doing. This is intuitive from the electronic system. The circulant matrix came from there. That is also a kind of transformation, and we are getting a matrix from there as we used to get from a linear transformation to matrix. The same way we have a matrix, which is a specific kind of matrix called the circular matrix. And if you have a circular matrix, then it have more property in compare of a simple or specific proper matrices also. What are the properties? This property is related to the eigenvalues and eigenvectors. And eigenvectors are easy to find there. Not easy means there we have to find the characteristic and solve the system of linear equation. Then we'll get the eigenvectors. But in the circular matrix case, it is just a, if you follow this formula, then it is going to be that. The eigenvectors are going to be, this is, if it is a, if your matrix is a circular matrix, then eigenvectors, we didn't talk about eigenvalues, we directly talk about the eigenvectors. Why? The reason is this property is related to the circular matrix, because if we have a circular matrix, we'll find the eigenvalues also with the simple basic method, right? Finding the a minus lambda I and do find the determinant of that. That would be done. Many of you didn't recognize in the interim exam your matrix is sorry, interim this uh, quiz 2 is given a matrix is a kind of circular matrix, and that could be easily find without doing anything. In quiz 2, if you remember, one question is there which is the given matrix is a circular matrix, and we I have seen many of you didn't recognize that is a given matrix a circular matrix, and you did all the process finding the eigenvalues, eigenvector, everything that the given matrix is a circular matrix. Surely one, see, we have a topic, then question would be there. If you recognize that, then just need to write the eigenvector, which is it's saying to be there. This is a circular matrix. Eigenvalues is going to be this, and eigenvector is going to be this. If you recognize that circular matrix, then the full marks will be given. But many of you didn't find that and started finding a minus using the way a minus lambda I. That's how the time it took also. Many people are saying this is the time issue also, but this is one question, not only one. There are, if the problem is given, some simple method is also available which could be done using that, if you recognize that. Long way is always available, but short method is also there. If you recognize, we got, so that's how the practice meaning. So again, we have in week 10 also a circular matrix, but maybe more, not only 3 or 4, maybe 4 cross 4, 5 cross 5. If you recognize that, that would be good for you. So if you have a circular matrix, so we can find the way as we used to find the eigenvalues, eigenvector. But if you just remember the eigenvector, this is going to be the eigenvector, which is uk. It's nothing but 1 upon root of n, n1 and omega k, omega 2k, where omega is here. That's all. And if you check the norm of each eigenvector, which is always going to be 1. To see it here, so this is the first lecture. We have seen already that mm, this is 1. So not only whatever if you have a circular matrix, then eigenvectors not only the norm of 1, also orthogonal. The eigenvectors are going to be orthogonal. Now norm is 1, so you can say orthonormal. Okay, so that is the in the DFT is actually that whatever the if you have a no 5 cross 5 matrix or 6 cross 6 matrix, so you can find the Fourier basis for that, and Fourier basis are going to be only those eigen vectors. Am I right? Anyone want to comment there? Is it? No. Why the Fourier word came here? Anyone? Now today is Thursday, and very few lectures are there in week 10. So I hope all of you gone through with the week 10 contents. Why the Fourier name is there, or not only why? What is a Fourier basis? Anyone? No. All of you are very silent. Anyone? What is the basis first thing? No. Okay. What is a Fourier basis? Why we are calling a Fourier basis, or what is a circular matrix? No one is answering. Okay. Okay. Yeah, so circular matrix is a specific kind of matrix. I hope all last time you have seen, we either you can see it here. This is a very some fixed number, you can say. We have some H0 to H7, and all entries are actually filled by these numbers only, and so you can see how it is arranged. If it is S0 to S7, then it is now H7 is here at the top, and now the rest all below of it will be same arranged here, H0 H1 same. Now you will take this H6 again and keep at the top here, in the third row, and now pick up this rest all and below of it write that. Now this is how the circulation is happening. This one is here, and then this one is here, and this is how circulation is. So this is a circular matrix, and have the eigenvectors like this only. If you just keep k is equal to 0 at any place, you will get here 1 1 1 1. So in the quiz 2 also there was a circular matrix and ask find the one eigenvalue and one eigenvector. You can just write directly 1 1 1 1 1 upon. If it is a 3 order, then you will just write the root 3, and you will get that easily. One liner. So here it is also, you can remember this formula. And now onward, only need to remember, if you remember the formula, you can easily do that. Now onward, week 10, 11, and also week 9. No, week 10 and 11 is exactly the formula is there. If you remember that formula, you can easily do. Because now the Fourier transform will come, you have to remember that formula. Simply, if you have a circular matrix, you can remember these are the eigenvalues, eigenvector, and you can do otherwise mathematically also you can get find the eigenvalues, eigenvectors as you used to find. But it will take time. It will not help you for exam. It will help for assignments, but in exam you have less time. So if you catch that is a circular matrix, directly you can write. So this is a formula, eigenvectors. So hope this is already done. I'm just giving the gist of 10.1. DFT. Now discrete Fourier transform is there in the second lecture. And what is a DFT? DFT is whatever the eigenvectors you got there. Now using that you will form a matrix. And this is how the matrix. See it? This is how you just write, as you used to do in the diagonalization. You used to find the eigenvector, form a matrix. That matrix itself, used to say P matrix or S matrix. Here we are calling DFT. But here first we have to find slightly changes there. Okay, see how it is. But the same thing is there. Okay, right side one is going to be your simple eigenvector matrix. So DFT is called transpose one. Now see how it is wrote. But eigenvectors are only there. Okay? And once you found DFT, I said no, eigenvectors are orthogonal of norm 1 only. So not only orthogonal, orthonormal. If you have a circular matrix, so eigenvectors are going to be orthonormal. So using that property, if you remember unitary matrix, last time we have discussed also, what is a unitary matrix? A matrix is called unitary matrix. U, I am saying U is a unitary matrix. If you do U trans Hermitian and U, you will get identity. So our DFT is a kind of unitary matrix. Why? Because if you do DFT, okay, this is the matrix, and DFT transpose, which is here, you can see it, you'll get identity. Your DFT is a unitary matrix. See, the same property is there. The reason is eigenvectors are orthogonal. Okay, unitary matrix is there. Now the case is how we'll find the eigenvalues. So that is a simple formula also. If you have this is a circular matrix, the eigenvectors corresponding to that is this one. Then use the property, eigen. If you have an eigenvector, if you have a matrix A and V is eigenvalue, the AV is going to be what? What is going to be AV? This is going to be a uh, some other vector, or this is going to be some scaled vector of V. Anyone? If V is eigenvector, anyone want to say something on this? If you have a matrix A and V is going to be eigenvector of that, I'm multiplying now A and V. What is going to be the right one? What is going to be the right side? Anyone? Raman, what you will say? Assis, Upendra, Chirag. No, are, are you there? Or
Yes, sir.
so what is going to be that? Somebody said that this is transpose time. It's lambda p. Okay. Yes. So it is going to be the eigenvalue time. This is lambda v. Eigenvalue time, the same vector. So by the same process, we can easily find the eigenvalues. So if you have this matrix, uk is the eigenvector, so lambda k vk. So if you follow that, you can easily find the formula for eigenvalues. So this is how it will go. So finally, what is going to be formula? These are all actually formula. So lambda ik is going to be h0 plus h1 omega k minus k to the power minus k, h2 omega minus 2 power k, until how it will run. These are going to be the eigenvalues. So you have to anyhow have to remember this formula. If you just do one or two more practice, if you do just practice, you'll get this. Even in exam, sometime you are writing this formula even. So only the numeric part is given. So very less marks would be deducted, and most of the mark will be given because you know at least. Only just need to keep the final numbers. But if you remember, that would be good for you to get the eigenvalues. So eigenvalue formula is simply S0 plus omega to the power minus k h2 omega to the power minus 2k, and this is how it will go. If you want to snip out, you can take the snapshot of that. So this is the formula we have. Even this one or below one, whatever you want, you can choose that. H0 H1, or simply this is the final H0 H1 omega to the power minus k, and H2, this is here, minus 2 power k. This will run through all. This is eigenvalue, easily we can get it. So this is the eigenvalues and eigenvectors. There is another concept which is called endpoint DFT. What is that? So endpoint DFT is, when we'll call the endpoint DFT is the length of vector. Endpoint DFT for a given vector, it is going to be what? Endpoint DFT is going to be the vector. This is a length n vector denoted by this one, where h0, h2, h till hn minus 1, because n is there, h0 is from running, so n till n minus 1 will run through, and this is going to be there, where hk is h time uk, where h is, so this is an inner product, where h is this one. You take the first column of the matrix, of the circular matrix, okay, and inner product with the, what is this, eigenvector. You will get each time hk. So the n point, 5 point, 6 point, 7 point DFT is going to be. So this is just a formula. The thing is there, if you just follow, so onward 10 and 11 is just formula, you have to follow that. Now see, what is a Fourier basis? Your eigenvectors only, nothing but your Fourier basis is nothing but the eigenvector of the circular matrix. Okay. And for any circular matrix, the eigenvectors are generally fixed. Eigenvalues are going to be changed. That's why this is called Fourier basis. That's why this eigenvectors are called Fourier basis, because if you're changing the circular matrix, eigenvectors are not going to be changed. Eigenvalues are going to be changed, but eigenvectors are not going to be changed. So that's why it is a kind of fixed thing, and you can call it as a Fourier basis. Now, these are just a formula. If you follow that, you can easily find. One of the important uh, lecture is this normal operators. Circular matrix is a normal operator. And what is a normal operator? Normal operator is, if you have a T, means the operators are generally written as a linear transformation from Cn to Cn. Okay, then it have, we know this one at finding the adjoint. If you have a linear operator from Cn to Cn, correct, we can find adjoint of it, right? This is also going to be from Cn to Cn. And how we'll get this? There are two ways, either using the inner product, or you can find the matrix representation, do the Hermitian, and write the expression. You can follow that, or using the inner product way. So there are two ways. People generally find this sort of thing. The simple way is find the matrix representation, do Hermitian, and write the expression. It is your T star or adjoint. Once you find the adjoint, so some operator have the property, if you do T star or TT star, this is a composition, okay? Remember that this is a composition, and T star T means commutative with respect to this composition. We have already seen the composition operator, sorry, composition of operators. So this is a commutative kind of thing. The operators are actually commutative. They are commutating with respect to the composition. And composition is nothing but the matrix multiplication. So if suppose A is a matrix of T, okay, A is a matrix of T, then so T star going to be nothing but a Hermitian. So if your operator is commutative, commutative means normal, then the matrix is also going to be commutative. This is what meaning of it. Means then you can call this matrix as a normal. So this operator is called, this operator you can call a normal operator. and this matrix you can call as a normal matrix. So the question is will arise why we are studying this. There is one, there are some properties for that. See, if you check it, all specific type of matrices are normal matrices. What are the specific type of matrices? Matrices are symmetric matrix, unitary matrix, orthogonal matrix. Okay, and real diagonal, you can say real diagonal matrix, circulant matrix. These all are actually normal matrices. All matrices have this property. A, you do Hermitian, it is going to be the same. This will hold by these all matrices. All this specific type of matrices are normal matrices. And what is the impact on this? The impact is why we are studying the second. This is one thing, one property. The second property, the main property is if we do this one, no? if you have a vector and apply this normal operator TV, whatever the vector will we get here. The if you find the norm is going to be unchanged. It is just flipped, but it will not scale up or scale down. Okay, length is going to be fixed. We see this is a theorem. Sorry, I missed that. Length with respect to t and t star both. So means if you are doing the adjoint, sorry, I just missed that. So adjoint, if you are applying, so if you're doing one side is on t, sorry u, and other side is on adjoint, length is going to be fixed. Sorry, I just left this side is just v. Sorry, so this is going to be t adjoint. So this is going to be fixed. Length is not going to be changed. While we are changing the operator means here adjoint of that. This is one important property of the normal operator. And some property it have no eigenvectors, eigenvalues. So what is the other property? The property is if you have an eigenvector v of t, okay, and the lambda is eigenvalue of that, then the same eigenvalue t star have, sorry, eigenvector have, but eigenvalues are just going to be the conjugate of that. Suppose you have a operator which is normal from Cn to Cn, okay, and V is a vector, eigenvector. Let's say our lambda is eigenvalue corresponding eigenvector is V. Then if you have a T star, okay, then eigenvalue for this one is going to be nothing but just conjugate of that, and same eigenvector will work for that also. Only the small change on eigenvalues, only the conjugate thing. Otherwise, all are going to be same. These eigenvectors are going to be same. This is another property of normal operators. Okay, proofs are there. You can check that. And the second property is if you have a two eigenvectors for normal operator, then they are going to be orthogonal. This is a beautiful property. So again, this is case for you can remember this by the same circular matrix are normal operators. So you can remember by using that. Say eigenvectors for that circular matrix are normal and or orthogonal. The same will follow with this normal matrices also. If you have two distincts, let's say lambda 1 which correspond to V1 eigenvector and lambda 2 which correspond to V2 eigenvector. So V1 is going to be orthogonal to V2 if you have This is as a normal operator. So more properties are there. Normal operators has a normal basis of orthonormal basis of eigenvectors. This is one beautiful thing, that if eigenvectors are orthonormal basis, orthonormal simply if you have a operator where the basis that basis or sorry basis I'm saying eigenvectors are orthonormal, then that operator is going to be normal operator. So this is a result. Okay, maybe there is a question would be asked on that. This is a question: you have a given matrix, or maybe you have a vector set of vector is given. Okay, let's say Vn, where set of vector where said that these are the eigen vector of operator t. Then option would be t is a normal, t is symmetric, t is diagonalizable, t is a lot more. So symmetric, di- diagonalizable, and uh, unitary. Sorry, not unitary. The matrix A corresponding to this T is normal matrix. Which option you will choose here? How many options are correct here? Anyone? Which options are going to be correct? The first option is T is a normal operator. The second is symmetric. Third is diagonalizable. Okay, P is diagonalizable. Okay, and A is a matrix corresponding to this T. Okay, then A is a normal matrix where this V1, V2 we have property all are orthogonal to each other. What are the options here correct? The sure thing is there. Anyone? Symmetric cases for A. A means the same meaning of A. Anyone? No? None of you have gone through with the content, or not able to answer, not able to unmute, not able to write in chat. Okay, that's all. Uh, Here in the content also. That's all in the week 10 also. All properties I have discussed. All of you try this question and let me know what is the correct answer. These are the properties we have, and rest all property we'll see later. Maybe not later. Almost we have done this week 10. Decomposition is the next topic, which I have wrote the third option there. I just left it for your practice. The third option is the same. The head topic is there. Will this be diagonalizable? Anyone can answer? No? Why the D option is not true? Why third option is true? Rihana? So, sorry, 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 I'm just wrongly pronunciation. Sorry for that. Right. So why the third option is not true? Then that is also going to be true. No, or not true. This is one of the property of the diagonalizable, sorry, normal matrix. Will the properties will that be diagonalizable or not always diagonalizable? Will that be never diagonalized? What is going to be that? Why you are very much sure that one option is the Raina? Others can also answer. No, others don't want to answer. Okay, that's all from my side. Anyone want to say something? Have any question? No, no question is there. Thanks everyone. That's all in the week 10 only. We have finished almost week 10. Okay. Thanks for joining. We'll see you on Saturday. Maybe Saturday is going to be the same time. It's 8 o'clock. Okay. Anyone want to ask something or any feedback or anything? Just unmute and comment on right hand chat related to quiz 1, quiz 2, income or anything. Okay. Thanks everyone. Thanks for joining. We'll meet on Saturday.